The second derivative test is very similar to the first derivative test, but what it does is it helps determine whether a function is a relative minimum or relative maximum. So let's actually return to the first derivative test just to do a quick recap, and we'll see why it's so similar. So if we remember, the idea was that if the function was increasing to decreasing, it helps us see that there's a maximum in between there where, again, there's a critical value which occurs at the min and max. We look at the derivative to the left and to the right to determine whether the graph is going from increasing to decreasing or decreasing to increasing would indicate a minimum. So kind of the change in the slope based on first derivative being positive or negative helps determine those things. But if you kind of re-examine the graph that we're looking at, notice that if a function nearby the critical value is changing from decreasing to increasing, that's actually consistent with a concave up curve, and vice versa for concave down. And that's exactly the idea in the second derivative test. It kind of is a simplification in a way. So let's go ahead and read it. It says, suppose that f is differentiable for every x in an interval and that there is a critical value within that interval. And again, that's kind of just saying, okay, we have a critical value. We're trying to figure out, is that a minimum or a maximum in between 2 points A and B. So we're sort of like, here's this critical value. Let's look nearby and sort of see what's going on to help figure this out. And it says for which f prime of c is equal to 0. So remember that a critical value is either going to occur when a derivative is 0 or when it's undefined. So we're just looking at the first case, the more common case, when it's just connected to a horizontal tangent line, slope of 0 of the curve. It says then 1 f of c is a relative minimum if f double prime of c is greater than 0. Or, remember, as we were just saying in the previous video, this means concave up. So what it's saying is that our value is a minimum if the curve is concave up. And part 2 says it's a relative maximum if it's concave down, if the second derivative is negative. So I'll just go ahead and write that on there, concave up. And just kind of as I was saying, if there's a horizontal tangent line on our curve and it's concave up, that means that value has to be a minimum because the curve is pointed this way. So the 0 value's got to be at the bottom. And if it's concave down, that means the 0 value has to be at the top. So again, it's very similar sense behind it. And it says, well, another case is, what if the second derivative happens to be 0? Then it says, in that case, the first derivative test can be used to determine whether it is an extremum or not. So it's sort of like, well, sometimes the test may fail, so try something else instead. And okay, let's look at an example. So let's let g of x be 1/3 x cubed plus x squared minus 3x minus 5. Again, we could go look at the graph, try to figure these things out this way, but our goal is to understand the first and second derivative test, so let's practice it that way. So what it says to do, first step is find the critical values. Just like with the first derivative test, we want to find those critical values. Remember, critical values are always where the first derivative is 0, not the second derivative. That's called something else. So first, to find the critical values, we take the derivative. So drop the 3, 1/3 times 3 is 1, and that would leave us with x squared. Derivative of x squared is 2x, and the derivative of 3x is negative 3. So our first derivative here is x squared plus 2x minus 3. We set it equal to 0, because that's always where the critical values are, either when the derivative is 0 or undefined. And then we'd need to solve when this is 0. I think I could factor this as x plus 3 times x minus 1. Yeah, that adds up. And so that means I'm going to have two solutions to this equation. X is equal to negative 3 and x is equal to 1. So here we have two critical values, negative 3 and 1. And then what it says to do is use the second derivative test to identify them as relative minimum or maximum. Typo, I should say as. Not messed up my grammar on the packet a little bit. But basically, once you have the critical values, now we can figure out, well, what's the second derivative and determine whether it's positive or negative nearby. Or not even nearby. We can determine, well, is it positive or negative at the critical value? It's even easier than that. So the second derivative of g would be 2x plus 2. And also another trend you'll notice with polynomials is as you differentiate them more and more, they tend to get easier and easier to deal with. Because you're losing every time you're losing the constant term, and every term is losing a degree. And that just means it's easier to work with. So naturally, it's actually a simpler process, and it's easier to figure out, easier to do math with. So you can see why the second derivative test is preferable in general when it works. So basically now what we just need to do is, again, these are like our C values. We just plug those into the second derivative. So what first thing is, well, what's g double prime of -3? Oops. So that would be 2 times -3 plus 2, which is -4. Notice that is negative. Again, negative second derivative, this means concave down by definition at that point. Which again implies that this critical value, which corresponds to a horizontal tangent line, looks like this, which means that this is going to be a relative maximum. We're not sure if it's absolute, but again, the first and second derivative tests don't tell us whether it's the absolute min or max, but it does tell us that we have a relative maximum point at f of c. And if you pay attention, it says f of c is the value. So if we were to go back, or in this case g, if we were to just figure out, well, what is g of c, that would be the actual, or g of 3 in this case, -3, sorry. That would give us the actual value of the maximum at the point nearby. And that would just be plugging 3 in here and running through the math. And sometimes you might be asked for, what is the location? Is it a min or max? And sometimes it might ask you for the value, but that's another step you'd have to do. Just plug it back into the original, see where it's at. But again, we're kind of imagining a curve where it looks something like this. Here's -3. And basically there's like a top of a molehill or whatever, whatever top of a hill at that point in time. Now for the other critical value, what about when x was 1? That was the second critical value that we had for our g function. Well, if we plug 1 in, that would be 2 times 1 plus 2 is 4, positive. And again, positive means concave up, which looks like this, which indicates a minimum. And this is the thing that's easy to get confused on, because notice that when you have a negative second derivative associated to a critical value, that's a maximum. It seems kind of opposite, but what I try to remember is concavity matches the sign. Concave up is positive second derivative. Concave down is negative second derivative. That's the opposite when it comes to that would be a relative minimum. And again, you can always remember, well, what does concave up and down look like? Concave up looks like this. That means there's a minimum on that curve because it's pointed upwards, and the 0 value would happen at the bottom. And again, you might say, okay, then also we know that g of 1 would be the local min value. And when it comes to business, you can see why all these ideas can be useful if we have a trending behavior of, financial graph, or our, product life cycle, or our revenue cost, profit sort of functions. It's a lot of times we're concerned with what's the high point, what's the best way, what's the optimization. All of those things are consistent with using first and second derivatives to find the points of interest. What's the high point on the curve?